First of all, we'll have Professor Wang from Hong Kong University of Science and Technology to do the presentation. Afterwards, it's followed by Professor Li from Chinese University of Hong Kong. And after the two presentations, we shall have around 15 to 20 minutes for Q&A. And at that time, if you want to have any questions, maybe you can just raise your hand in the Zoom meeting account, and then we will unmute you to let you tell us your questions. And the two professors will pick up your questions and answer, right? So without any delay, I'll pass the mic to Professor Wang to do the first presentation.
All right. Thank you very much. It's my great pleasure to be here. Great pleasure to in front of so many participants online. And today, I'm going to tell you about the universe. And what is the universe? Before talking about anything about the universe, let me first start from something more familiar, all right? Start from our Earth. And this is a photo that I think you have some sense of familiarity. This is the Earth. And where did we take this photo? This photo was taken on the moon orbit, okay? So it was the Apollo spaceship taken this photo on the moon orbit, and this is our home, okay? Everyone's home, and this is the Earth. And the name of this photo is the Earth Rise. And from this photo on, we can actually zoom further to the boundary of our solar system. And this is another famous photo. This was known as the Viagra spaceship moving to the boundary of the solar system. And that spaceship was meant to explore the solar system, and outside the solar system, the camera was pointing outside outwards the solar system. But at this moment, the scientists and engineers decided to point the camera back to take a look at the whole family of the solar system. And this is what we see. Here, the photo is extremely tiny about our Earth. And let's take a little closer look at what is that very little blue dot, all right? That very little blue dot over there is our Earth, okay? This very little blue dot, that takes only 0.12 pixel on this image, okay? And this is not even a pixel, and this is the Earth. And here, so the best description is by Carl Sagan, and let me just quote him, that look again at that dot. That is here, that is home, that is us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. And this is our home, and this is the only home that we have ever known. Excuse me, just agree. So, if you zoom our image to a further position, we see the Milky Way, okay? We see our Milky Way, and this is not actually a photo which we actually take, because so far, there is no spaceship which can fly as far as the boundary of our galaxy. However, this is actually a photo based on a combined photo based on our current observations. And actually, we are pointing to something, and that is the position of our solar system. But I have to tell you that actually, the solar system is not even 1 pixel in this huge image of our Milky Way. And further, if we zoom our image further, we can get further things. But here, let me mention that there are hundreds of billions of stars in our Milky Way. And what do I mean by hundreds of billions of stars? Here, I'm mentioning 100 billion. I'm sure that everybody, that you can count numbers, but have you ever count to as large as 100 billion? Nobody has. We don't have an intuition about what this number means. What this number means, there is a poet, English poet William Black. He says to see the world from a grain of sand. Okay, let's just imagine that our solar system is just a grain of sand. In this case, what corresponds to our Milky Way? That corresponds to hundreds of tons of sand. Okay, a grain of sand versus hundreds of tons of sand, which can fill many of the heavy trucks. This is what our solar system versus our Milky Way means. And then let us zoom even further outside our own galaxy to the whole universe. All right, this is the size of the whole observable universe and a small selection of the galaxies that we have observed from a number of telescopes. And actually, it happens that the galaxies that we can see in our observable universe, I will explain to you what observable universe means, but within our observable universe, the number of galaxies is also around hundreds of billions. And this is our universe. Our universe is one of the most complicated, is actually the single one of the most complicated object in our universe. This is because all the complexities in our universe is contained in the universe, okay? Everything complicated contained in our universe, but it's really amazing that Einstein says the most incomprehensible thing about our universe is it is comprehensible. That hopefully we can understand our universe. We can understand our universe by our observations without having to understand everything in our universe. Okay, first, let's think about our universe and think about what the word universe means. Okay, what it means. Let's first understand it literally, that we separated to uni and verse. What universe means is to turn everything into one. And what verse means is to make into. So uni means one, and verse means turn into. So if we turn everything into one, and that will be our universe. Okay, this is the universe. And in the Chinese characters, that means the first character means the space, all the space, everywhere, the space. And the second character means verse, means the time from the ancient past to now and the future, all the time, all right? So all the space, all the time, and all the matter in the space-time, and this is the universe. And the science of cosmology, is to study our universe as one object. This is what we are talking about, our whole universe, all right? And the first question we would ask about our universe is, what is the matter in our universe? Actually, the matter that we are pretty familiar with, okay? The matter which are made of atoms. So you probably have ever known that Feynman ever says that the world is made of atoms. And this is one of the most important thing, most important message. But the matter which was made of atoms actually just take no more than 5% of the matter in our universe. And there are 25% of dark matter. The dark matter that we know, the gravitational interaction, we know the gravitational attraction between the dark matter and us, but we don't know in their particle nature what particles they correspond to. And there are even more, around 70% of the matter which was known as dark energy. And that dark energy, we don't even know what they are, okay? Even their gravitational interaction is different. In some senses, not even gravitational attraction, is repulsive force in some sense. It's so complicated, we don't know them, but we can feel them through gravity. This is dark matter and dark energy. But let's start by talking about the 5% that we understand. In this 5%, there are about 4% are just free hydrogen and helium, okay? That 4% is just spreading in the universe, and for sure it is very important for astronomical observations, but it's not so interesting from our imagination. For our imagination, the interesting thing is about 0.5% of the stars, and also light, okay? Our observable light is 0.005% of our universe, and etc. So the matter that we are familiar with actually takes a very little percentage of our universe. And our universe is very empty. Our universe, the average density of our universe is about 1 atom per square meter, okay? It's extremely low density. Excuse me, it's very difficult to imagine from our Earth, and actually it's even more difficult to imagine from Hong Kong, all right? It's just 1 atom per square meter, per cubic meter. It's extremely low energy density, and this is our universe, all right? So having understood what is the status about our universe, what is the dynamics, okay? How our universe evolves with time. What is the dynamics of our universe? And the most important dynamics of our universe is the expansion of our universe. What do I mean by expansion? Here, first, I invite you to do this problem. I'm sure every of you can do this problem. However, if your math is taught by a physical teacher, maybe you can do the problem in another way. And actually, this is the way that our universe does this problem, that imagine that every element, every matter in our universe is like this A and B, for example, atom, and for example, even as large as galaxy. Okay, they are like this A and B, so they keep their size unchanged. However, the space between the galaxy clusters, the space between these galaxy clusters emerges, and that was known as the expansion of the universe, which we have already known almost 100 years ago by a few pioneers of cosmology, for example, Hubble. And the expansion of the universe nowadays, so at the moment of Hubble, he interprets that the distant galaxies are moving away from us, but nowadays we understand it as our universe expands as a function of time. This is how the Einstein's theory of general relativity works. Okay, so this is one part of my talk, and let me briefly recap so far that we have been talking about what is our universe, okay? So that is everything that turns into one, that is the space-time, and everything in our space-time. And what is the matter in our universe, okay? So that is the atoms, that's light, dark matter, and dark energy. We don't know, we don't understand dark matter and dark energy very well, but that takes about 95% of our universe. And the thing that we understand only takes about 5%. And what is the dynamics of our universe? The most important dynamics of our universe is the expansion of the universe. universe expanding, become larger and larger. So this is our universe. And the next question that you'd like to ask is, how old is our universe? Was our universe always there? Or it has some sort of creation time? Before answering this question, I'd like to invite you to think about the following question, which was known as the so-called Outburst Paradox. The question is as follows: that you imagine we divide our galaxies into shells and shells, okay? The shells closer to us and the shells more distant to us. In this sense, think about the closer shell and the farther away shell. Do they appear to be as bright as each other, or the closer shell is brighter than the farther away shell? If we just think very quickly, we might naively thought that the closer shells of the galaxies, of the stars, are brighter, overall brighter compared to the farther away shells. That is because, yes, for individual stars, okay, for individual stars, if they are closer, definitely they are brighter. However, what if you think about the number of stars, okay? For the nearby shell, there are fewer stars, okay? For the more distant shells, there are more stars. And actually, both the intensity, the brightness of the stars, and the number of stars is related to the R squared, the distance squared between us and the stars, that the number of stars is inversely proportional to R squared, and the intensity of stars is proportional to R squared. What that means? That means that the overall intensity, the overall light that you emit from these stars is more or less a constant. Okay, then there is a problem. There is a paradox that wouldn't our universe become infinitely bright? Okay, wouldn't our brightness of the universe be infinite? Because the nearby stars contribute the overall intensity of our night sky in the same way as the distant stars, okay? Then how would that be? How that could happen, all right? And actually, if you find there is a problem, so first, did you find there is a problem that this is known as the Outburst Paradox, that why our night sky is dark, okay? It appears that otherwise our night sky should be as bright as at least the nearby stars, okay? Why our night sky is dark? And you notice there is an implicit assumption in this Outburst Paradox that we are assuming that our universe in all senses is infinitely old and infinitely large, okay? So first, our universe is infinitely large, otherwise there is no Outburst Paradox, all right? If our universe was not infinitely large in some sense, okay? I haven't mentioned in what sense. I will mention to you in what sense, but if our universe was not infinitely large, what that means? That means, okay, so we truncate our universe at some certain position, and in that means, actually, you are not going to see infinite shells of stars, and you are not going to see infinite brightness of our universe. All right? So one resolution of the Outburst Paradox, why our night sky is not infinitely bright, is that in some sense, our universe is not infinitely large, all right? And in what sense? And actually, you probably already know the Copernicus principle, that the Copernicus principle says that we are not the center of our universe, all right? That generalized Copernicus principle is saying even our solar system, even our Milky Way is not the center of our universe. If you assume the universe as a finite size, are you saying that we are at the center of our universe? Which doesn't sound right. Okay, I'm not saying so. I'm saying in some sense. And in which sense? If let us imagine that our universe has a finite age, all right? What do I mean by our universe has a finite age? That means if our universe was born about 10 billion years ago, okay? In this case, what happens? In this case, considering that our speed of light is finite, okay? You know, speed of light is finite. And if our universe has a finite age, that means the observable size of our universe is finite, okay? And what that means? That means if there are light from some galaxies, that even from our creation time of the universe, actually there are no galaxies at that time, but even you imagine, even from the creation time of the universe, the light is trying to propagate to us, and now the light haven't reached us yet, okay? If the galaxy is very far, it's far away enough. That means the observable size of our universe is finite, okay? And the so-called edge of our universe, there is no physical edge, okay? As far as we observe, there is no physical edge, but considering that light is going finite speed, that means if we look further in space, okay, we are looking at earlier in time, and that so-called edge of our observable universe corresponding to the birth time, okay? Corresponding to the time that our universe was born, all right? So from our observation of the universe, we infer that our universe has a finite age. And we can infer the finite age of our universe not only from the Outburst Paradox, but also from a lot of other ways, including, for example, from the earliest object, the oldest object in our universe, for example, the cooling of the white dwarf, and also from our finite temperature of the initial universe, what would be the temperature, and from a lot of other ways. From these ways, we infer that the age of our universe is 14 billion years, okay? And what is 14 billion years? Again, it is an extremely large number. And if we compress this 14 billion years into 24 hours, just imagine we make a film of 24 hours to describe the whole evolution of our universe in this 14 billion years up to so far. And that means the whole human civilization corresponds to less than 1 second in that 14 billion years, okay? And so we are talking about the age of our universe. And as a quick recap so far, what we have been doing is how old is our universe? That's about 14 billion years. And that can be got from the Outburst Paradox, from the temperature of our universe, from the oldest objects of our universe. And at this point, you may ask me the question, how large is our universe, okay? Then we have been talking about the size of our observable universe. The size is known, is about 45 billion light years. And that follows because of our age of the universe was known. And on the other hand, the absolute size of our universe is unknown, okay? Beyond the observable part of the universe, how large is the rest of the universe? Or even, is it finite size or is infinite size? Einstein, in the past, conjectured its finite size is three-dimensional sphere, but actually we don't know, okay? We don't know even our universe has finite size or infinite size, not even to mention how large is our universe absolutely. We don't know, all right? So this is about the age of our universe. And when we are talking about the age, we are talking about history, and we'd like to talk about what is the history of our universe. And when talking about the history, I'd like to invite you to review a very elementary physical phenomenon, which is if you do work to gas, okay, the gas will be hotter, okay? If you compress a box of gas, the gas becomes hotter. And you can think about this problem in the other way around, that if you expand a box of gas, that box of gas becomes cooler. And this is what happens in our universe, that originally our universe was in extremely hot state. Why? Because currently our universe has a small, it's a 3 Kelvin, it's a small, but it's a finite temperature, okay? Our universe now has a temperature, and then think about the past of the universe. Let's track back in time. And we track back in time, that really looks like that we are compressing a box of gas, okay? Track back in time, the same volume in our universe becomes smaller and smaller. That really looks like we compress a box of gas. And once we compress a box of gas, what happened? We just mentioned that our box of gas, our universe becomes hotter, all right? And once our universe becomes hotter, what happens? All the high temperature, high energy physics happened in our infant universe. And actually, it is generally believed that our infant universe was hotter than any of our current experiment can do on the Earth. Our universe was in an extremely hot state, and in the very beginning of the universe, actually so far, we don't know how our universe got started from our cosmology study, and then we know something. We know inflation, which was an exponential expansion stage of our universe. And after inflation, what happened? We don't know. How our universe got heat up from that exponential expansion of the universe, we didn't know. And then at about 20 picoseconds after our universe was created, there was the origin of mass. How mass arises, for example, where the electron mass come from, and that corresponds to a so-called electroweak phase transition. So that may seem odd to you, but the 2012 Nobel Prize, which was given to the discovery of the so-called Higgs particle, and that particle is actually what's known as related to the mass generation. What is the origin of mass? Where the electron mass come from? And then at about 20 microseconds, there was the so-called QCD phase transition, which corresponds to the proton and the neutron, how they were formed. And then 400,000 years after our universe was born, there was the first ever light which can propagate in our universe, and then the first galaxies. Okay, what do I mean by the first ever light? Let me first talk about what do I mean by the first ever light. That means that when our universe was in an infant state, extremely early state, at that stage of the universe, our universe was so hot. Our universe was so hot that the matter in our universe was in a state of plasma, okay? What do I mean by a state of plasma? That means a state where there is no atom, okay? There is no conventional atom that the electron is bounded around the nuclei. And the state of a plasma is that the nuclei is flying around, and the electron is flying around independently because of the high temperature. So the electron cannot just be combined into the nuclei, into the atom, around the nuclei, into the atom. This was the very initial state of our universe. And as a result, the electron is flying all over everywhere, and light can so frequently hit the electron and get scattered. And that means in a plasma state, our universe was opaque. Our universe was not transparent, all right? So this was the infant state of our universe. And as our universe expands, as we mentioned, when our universe expands, the temperature of our universe becomes lower, and at a point, the plasma state becomes an atomic state, okay? The electrons get combined into the atom around the nuclei, and then there is no free electron anymore, and the light, for the first time, can travel through our empty space. And that moment is the moment that the first ever light arises, okay? So that explains to us where our first ever light comes from. The last slide, previous. This explains where our first ever light come from. And actually, in our early universe, because it's about our so high energy states, there are so many origin problems which can be answered in our early universe, including, for example, where the first ever elements come from, okay? So at the very initial stage of our universe, we have protons, we have neutrons, and how these protons and neutrons, how they combine into elements, for example, into the helium elements, for example, into the helium elements and into the lithium elements, how they combine into elements. And that is through the Big Bang nucleosynthesis, okay? When the temperature becomes lower and lower, eventually there is the Big Bang nucleosynthesis that the protons and the neutrons combine into elements, where elements originate, where elements come from. And I have been talking about where mass comes from. So we can answer so many of the origin questions in our primordial universe. And the next question that we'd like to address is where structure comes from, okay? So our current universe arises as full of structures, okay? Our current universe, there are so many things in our universe. There are galaxies, galaxy clusters, etc. And Professor Lee will further talk about some smaller scale structures in our universe, okay? Our universe was full of structures, but where these structures come from, okay? And actually, there can also be an origin. We can also find the origin of structures in our universe, such that when we look at the first ever light in our universe, we have just talked about the first ever light, that our universe originates from an opaque state, okay? Our universe from a state where light cannot freely travel to a state that light can freely travel, okay? And then we can observe the first ever light in our universe, and you imagine that corresponds to a sphere that we can observe, and that is known as the CMB, the cosmic microwave background. From the first ever light, from the cosmic microwave background, what we can observe, okay? We can observe is almost isotropic. That means almost every direction we see the same temperature. However, there is a little small difference in temperature. There is a so small difference in temperature is 10 to the minus 5, okay? So that means 1 part in 0.1 million, okay? Extremely small fluctuation in that the first ever light. In one direction, the temperature is slightly higher. Another direction, the temperature is slightly lower. By slightly, I mean really slightly, just 10 to the minus 5 higher or lower compared to anywhere else, okay? So there is teeny small fluctuation from the cosmic microwave background, and that teeny small fluctuation is the origin of structure. All right, so here you may get confused, you may feel curious. Okay, so currently the structure is so huge, okay? But you are saying the origin of the structure is 10 to the minus 5 fluctuation. Okay, how this little, teeny, small fluctuation can arise our current structure in our universe? How? Actually, this is because gravity is unstable. That imagine that there are some matter. Originally, there are some very small over density, meaning that the density in this part is slightly higher. And then what will this part of matter do? Okay, this part of matter will attract other parts of matter. Excuse me. This part of matter will attract other parts of matter. So matter will be attracted to here, and this part will become higher and higher density. And then the other part will become lower and lower density. And as a result, then eventually our universe, from a little bit of fluctuation, a teeny small 10 to the minus 5 over density, 10 to the minus 5 difference in temperature, become a fully structured universe. And here, let me play a video for you for this fully structured universe. Originally, we start from a universe where there are little structures, and then, so this is a scientific simulation. It's a simulation of the large-scale structures of our universe. From the universe where there are very little structures, we step by step, because of the gravitational instability, the structures develop, and eventually we end up with a universe full of structures, full of galaxy clusters, and also galaxies. So this is our universe. And as a recap of this part so far, we have been talking about the earlier, the hotter. If we think about the earliest stage of our universe, that really looks like we compress a box of gas, and that corresponds to a hotter stage of our universe. And then we have been talking about the origin of light, and also the origin of light elements, okay, where our first ever light comes from. The first ever free light comes from the that our universe transit from a plasma state where light cannot freely travel to a state where the electron combine into atom and light can freely travel, and where our light elements come from, that's from the Big Bang nucleosynthesis, and where the structures in our universe come from the gravitational instability, that originally our universe has a little bit of structure, 10 to the minus 5 over density, and then that gradually grow into our structure of the universe. Okay, so as an overall recap of what I have been mentioning so far, we have talked about what do I mean by the universe. Okay, put everything into one, and what are the components of our universe? We know 5% of the components, and there are 95% where there are 25% of dark matter. Dark matter is what we cannot see, but gravitational nature is the same as ordinary matter. And we have dark energy, again, we cannot see. Even the gravitational nature is different from ordinary matter. We talked about the expansion of our universe. We talked about how old is our universe, the age of our universe, and we talked about the size of the universe, how large is our universe. That actually we don't know how large, but we have an idea of how large is the observable universe. And we talked about the origin problems that look further, look distant in the universe, we look earlier, okay? If we look earlier, we look hotter. And there was a stage that starting from the cosmic microwave background, starting from our universe from plasma to atomic state, light can freely travel in our universe. And also there is the structure where is the structure of our universe, how the galaxy clusters form. But we still don't know a lot of things about our universe. For example, what is dark matter in our universe? What is dark energy in our universe? What is the origin of our universe? And if we evolve further with time, what is the fate of our universe? There are a lot of things known in our universe, but equally, there are so many things that we don't know in our universe. All right, that is my part of the talk. Thank you.
Okay, hi everyone. This is the Hua-Bai Li from CHK. Okay, I'm going to continue the cosmos picture Professor Wang showed us and try to bring everybody to us. Okay, so Professor Wang started with zooming out from our own solar system. So I'm going to first review by zooming in back to us from the cosmos. Okay, as we just learned, from the CMB, we can learn the mass density fluctuation from the early universe. And if we believe in the assumption of dark matter and through the gravity, we can develop a lot of the current large scale structures. So I'm going to show you another simulation here. Okay, start with the density fluctuation inferred from the CMBR. Assume dark matter, and also on top of it is regular mass, which I showed the gas here. Okay.
12 million years after time zero, and evolves within a volume 350 million light years across.
So first, again, we see this spider web kind of structure. It's mainly this gravitational well carved by dark matter. Okay. But from this point, when we have this gravitational well, we can create galactic clusters, right? But if we want to go even smaller scale, right, we want to go to smaller because we want to move toward us, right? We are so small. If we want to develop even smaller structures, we need those regular gas, because regular gas can further radiate, so they can get even colder. I've just learned, right? You want to get smaller and smaller, denser and denser, you need to be getting colder. Regular matter, they radiate, so they can get colder. And thanks to Professor Wang, we can move forward. We can go to another 10 billion years. Okay, so I have 10 billion years right at this point.
The coming together of dark and ordinary matter.
Ordinary matter.
That heat up as gravity compresses them.
So now we're zooming.
That leads to the production of metals and stars that are spread throughout the cosmos. Finally, there is light, given off by ordinary matter in a variety of wavelengths that we can record from our tiny outpost.
So again, this is not a cartoon. This is a real simulation based on physics equations which govern gravity, right? And also based on the initial density fluctuation from observation. And based on just this, we can all the way process to, like this one shows here, an individual galaxy. Okay, this is what we have learned so far. We take both dark matter and regular matter to reach this point, right? But individual galaxy. Then how about from here to us? What do we keep on running the simulation I just showed you? Actually, we would go far from reaching us, right? Starting from this point, the simulation becomes very complicated. And not to mention about us, we almost cannot create any further small structures which is comparable to observation. So The rest of the talk, I focus on our effort to try to understand these smaller structures, right, from galaxy to individual cloud, to individual stars, to planet, and to us. But it's full of questions. Right? Okay, so to us, first we have to know what is us. Right? What is us? Okay, we are showing the figure in the left-hand side. We are in the center, and we see lots of materials that we need in our body. You have iron in your blood, your calcium, your bone, and you take a look at those vitamin pills you probably take daily, the magnesium, zinc inside. Right? These are materials our body needs. And you will remember the talk from Professor Wang, during the Big Bang, the nucleosynthesis will give us only helium and lithium, hydrogen, of course, right? But nothing heavier than lithium. So where can we find these materials to put into our body? Where can we find calcium ions? They are not formed in the beginning of the universe. And in fact, you can only find them, and they can only be forged with a massive star. With the mass of the massive star, the compression due to the gravity can fuse these lighter material like hydrogen, helium to heavier and heavier elements. Okay, so we believe that those material, heavy elements our body needs are actually coming from massive stars. And the question is, how can we get material from interior of massive stars? Right? We have to wait until the star dies. Okay, for massive star, they will die with explosion. You probably heard of a supernova. Right? Supernova, they're actually the death of massive stars. And when after this explosion, the interior of this heavier element within a massive star, they're going to be redistributed into the medium of the galaxies or interstellar media. And then somehow, through the process we're going to talk about more later, these galactic materials, which mixed with this heavier element produced by massive star, they are going to process into newborn stars, planets, and eventually you and me. Okay, so you guys are probably too young to ever watch this soap opera. I didn't either, but I think this is the most scientific title of a soap opera ever. Right? Even though I don't know what they are playing in it, but the title is really scientific. Most of you, all of you, and me are all from stars. So the rest of the next slide, I'm going to zoom into the two processes. It's the blue process and the green process. There's lots of detail within it. Right? They are showing here. So the blue process, that basically how star grow, how star developed from a baby phase to teenager phase and to their death. You probably heard of a white dwarf. You probably heard of a neutron star, black hole. There are different type of deaths of stars. But they are very less massive, like our sun. They might die as a white dwarf. But if they are very massive, they can die with explosion and to turn into neutron star or black hole. Right? Another process is to going from this diffused media in a galaxy. How can they get fragments, get denser and denser, and eventually get as dense as a star, so they can start the nuclear fusion to form heavier element for later redistribution into back to diffuse phase. And so there are two basic different kind of process. Right? The from the baby star to the death of a star, this is very well known. This is called stellar physics. But the other process, how can we process the diffused media all the way to star and to planet? This is not very well known. This is called star formation. Okay, so if in the future you go to study in the university department of physics, you are going to learn all the physics you need to explain the life of a star, which is stellar physics. You are going to learn quantum physics, which explain how the energy can be released from the center of the star while they are forging lighter element to heavier one. Okay? And then because it's burning inside and the star is basically a giant sphere of gas, so when you're burning in the center of the gas, this blob of gas is going to have convection, right? How this flow goes on under this heating within, and this causes the hydro equilibrium, and it's governed by classical mechanics. And then of course, the heat or energy formed inside the star is going to propagate to, for example, us, right? So we get all the energy from the sun. So this energy propagation is governed by thermal physics and electro and magnetic physics. So it's what's called 四大力学, right? If you go to Department of Physics, spend 3 years there, you have to be able to explain the whole life of a star. Okay, so this is very well known, but for the rest of our talk, we focus on more unknown things, right? Which is star formation, which is the first step we have to understand in order to know where we are from, how we are formed. Okay, so for star formation, we have to take a look at the star, right? And this is a photo from mountain in Taiwan, and you see the whole Milky Way. You can see very similar kind of thing if you go to the cyclone during the summer night. And along with lots of structures, we see not only the stars, but also some dark lenses, right? They are actually those regions with higher density of gas, which we call gas cloud or molecular cloud. And I just pointed 2 of them as our reference. So through the talk, we're going to visit back to these 2 references quite often. Okay, so if you want to learn how stars form, we probably want to visit probably younger star, right? Not those very old stars. Just want to study the birth, right? We visit younger star and also study their property and their environment. Hopefully, we can figure out something. It's just another view of our Milky Way. And again, our reference shown here. And also in the lower right is Orion. And most people should know Orion, right? So we can zoom in into Orion to see the detail of the environment of a baby star. So here we have a video of zooming in. It's mostly dark, but a very bright cloud in the middle. Look like a bubble. You can see a shield here. And kind of in the center of the bubble is very bright. Keep zooming in, become very foggy and hard to look into it. All right, so if you want to see what, we have to find some way to look into this foggy environment, right, to see what really happened inside, because it might be the site which is closest to star formation. Okay, so how can we see through this fog? And here's a pair of photo taken at the same time to the same spot to a gas room full of tear gas. And we're now very familiar with tear gas right after last year. And the left-hand side is just what regular human naked eye can see, right? You don't see what happens inside the room because all the light are blocked by fog, smokes. And you just see the surface of the smokes. But the right-hand side is the photo of the same room, but take at different frequencies, taking the near infrared. And you can see what happens inside the room. You see 5 guys inside the room. Okay. So what happened here is actually, we call it the thermal emission, which is everything is given away light. But the frequency of light depends on the temperature of the object. So we know that our sun's giving away the rainbow-like light, right? It's because the temperature of the surface of the sun is about 6,000 degrees. Okay, so at this temperature, it will give away light like in the rainbow range, and also beyond the rainbow. Beyond the red, we call it infrared. Beyond the violet, it's the ultraviolet. Okay? But the peak, the range, all depends on temperature. And for our human being, we also have the temperature, right? If you're healthy, probably it's 36 degrees Celsius. Right? You are also given away light. Just this light cannot be catched by our own eyes, but you are giving away light. You are giving away light in the infrared side. So what the infrared camera caught in this photo here are the light given away by our human being body. Okay, so the camera don't depend on to see the reflection light from the body, which is blocked by the smoke. It can detect the light from the body directly. So with the same kind of strategy, we can try to look into the star-forming cloud. Again, these 2 photos in below, they are the same point of view of the so-called Horsehead Nebula for apparent reason, right? So left-hand side is optical, taken by Hubble telescope, and you see a dark cloud. And right-hand side, look at near infrared, and you can look through the cloud and to find the closed environment of each stars. And when you apply this kind of strategy, what do we see? Deeply embedded inside this cloud. Here's one example. Recall the background milky light is from our previous zooming in to the Orion Nebula, right? But if you change the view to infrared, you're going to see these newborn stars buried deeply inside this cloud. As the red things are newborn stars looking at the near infrared. And more interestingly is that you see all these kind of newborn stars, they are accompanied by a disk. So these are face-on disk. So the circular, and when we look at disk, the edge on, they become these flattened structures. Okay? And if you compare our solar system with this disk, you see the size are quite comparable. Okay, so we believe that these kind of disk structures, they are the site of newborn baby stars. So we call them the star's cradle. So we are getting closer to the star forming site. And now at least we know what's the next step of the structure should be developed into in order to give the birth of the star. And so far we learned that when gas getting colder, gravity will bring things get denser and denser. Well, this baby star doing weird things. They actually spit things out. Like here, again, it's an hadron disk. But for this hadron disk, we see this green light coming. Well, you might wondering, how do we know it's coming out, not falling in? Right? But here is a continuous photo taking one of these jets within 15 years. And you can clearly see that the jet is moving from lower right to upper left, right? While the star disk is located in the lower right. So it's moving, shooting out from the disk. Okay, these are all the properties of these newborn baby stars. Some properties we observed. Okay, and we apply the same strategy, right? Looking at different frequency, mostly toward the infrared size. If we zoom out, again, from this spot, which is where we zoom in, and if we zoom out, we see the entire Orion. Okay? This, again, optical frequency, but we apply the same strategy. What is Orion would look like in infrared, and more particularly in far infrared. And this is how Orion looks like in far infrared. Right. So as we learned that only the hot stuff, right, like sun, several thousand K, they're going to give out the rainbow light, which can be picked up by human being naked eyes. Right? And all the black dark sides here doesn't mean there's nothing there, only means that our naked eye cannot pick up those light given out by this stuff. And what are those stuff? Right-hand side showing some example of them. So when tune our frequency to far infrared, we can see so many of stuff. And they are mainly those thermal radiation. Again, like our body have thermal radiation. So this kind of dust grain also feel the thermal radiation. Okay, so when we tune to the right frequency, we're going to see them, and you see they're everywhere. And not only so, you also almost see the correlation between the location of stars and the dense collection of dust, right? Like here and here, dense, a big block of dust, and we see stars. Okay, and if you learn those thermal physics, ENN physics, then you will be able to not only see them, but you are going to able to estimate the mass of this gas and estimate their temperature. So we do so, we find that the total mass involved in this Orion collection of dense of gas is as massive as 100,000 of suns. And the temperature is very low. It's only minus 250 degrees Celsius. And the size is about 10 PC. Don't know, maybe you don't know what PC, but 1 PC is about 3.26 light year. You must know light year, right? So the size is about 30 light year. And when you have these informations, density, temperature, and their size, right? We learned from the previous talk that we can predict how they are going to develop under gravity, right? So we just like we see how the galactic cluster are developed under the gravity of dark matter. Here we can do the same thing, and to predict that everything we see here, these materials are going to fall together to one point because they fall into each other within 1 million years. Okay, if it's only gravity apply to this chunk of gas. But the reality is we can also estimate the edge, which we cannot cover here, but astronomers can. The edge of this cloud is much, much longer than 1 million years. And if we calculate the stellar mass within this map and compare to the mass of the gas or the cloud, stars is only a few fractions of the total mass of the cloud, which means that they're certainly not going through free fall. There must be other force against gravity, against this gas fall into together, right? So turn everything to star. Just a few percent can reach star during these years, much longer than the free fall time. Okay, so this becomes the first question the star formation theory have to answer is why don't these gas, they fall into each other? Okay. Actually, they form very few, just a few fraction of them fall into each other. The rest of them just stay quite pretty much in the same space. Okay. So far, we collected some questions about star formation we have to answer, right? We have to explain why the star formation rate is so low, why they don't go through free fall, and how this and jets are forming at the end. Okay, and also an important question we have to answer is the so-called initial mass function. What does it mean? It's just like the distribution of the babies, massive baby stars. If you take a look the newborn baby weight of Hong Kong, you probably see a distribution, right? The peaks probably, I guess, will be around 3 kilograms. Okay? But when you look at the star, they actually also have some mass distribution. You look at Orion, look at Pipe Nebula, or you look at, say, any other cloud, they might give birth to 1,000, 10,000 stars, but all the clouds, they have the same mass distribution of stars. The most popular mass happen to be the solar mass. You will find the fewer stars that is heavier than our sun, and also less star, which is lighter than our sun. So why is that? Why the solar mass is the preferred one? This also needs explanation, right? So all these are the star formation theory try to answer. And the answer is we don't know. We haven't there yet. But the rest of the talk, I'm going to show you what we do know, right? How close or how far we are from explain this phenomenon based on the physics we know. Okay. So first, an important discovery is that we found that those gas, right, we just seen in Orion or any other dense cloud, they are moving very fast for some reason. Right? Certainly not due to the temperature, right? Because the temperature is so low, but somehow they're moving very fast. Like the video showing the left-hand side here. These are also another cartoon. These are also numerical simulation based on the observed parameters. Okay, and they're not only moving, but moving very fast. They are actually supersonic. What would supersonic motion do? If you ever seen a supersonic jet fighter, which we can go to the Zhuhai every 2 years, you might have a chance to see this, right? Why the jet fighter reach the speed of the sound, you will see it will compress the gas and form this higher density region which light cannot go through. So you see kind of they're creating this cloud. Okay? And because the motion is supersonic inside this cloud, so they will also create lots of the supersonic shocks, which you see in the purple color here. Okay, and because they are moving so fast, of course, they are not moving to the gravitational well center in a free fall velocity. Okay? So this discovery can first explain why this cloud does not disappear after a million years, right? Because they're moving so fast. They are not falling to each other. And this is called supersonic turbulence. And you can see it's very complicated, right? So it's very hard to understand the behavior. Even Heisenberg also agrees so, right? Turbulence is really difficult. But at least we know that's why the cloud doesn't go through free fall. Okay, so one more property we know. So far we know the mass, the density, the temperature, and now we also know the internal velocity. Okay? So we are moving forward. What else we know? Well, here's one discovery we have in the CHK. Again, we come back to the pipe and Ophiuchus here. Right? And for a long time, astronomy are wondering why these two clouds, they're very similar in temperature, in density, and in the velocity, turbulent velocity field. They're all very similar. But why is one of them give lots of baby stars? Like this one, you see it's colorful nebula. They are due to the stellar feedback from the stars within. And the other is the pipe. The neighbors or even twin sisters, which doesn't give much birth of babies. So it's a puzzle astronomy for a long time until we try to show the magnetic field. So this is another thing, new thing we learned today, right? Is this cloud is not only moving very fast, very cold, but they also possess magnetic field. So here again, this is the pipe. We see the red lines are the magnetic field that we detected. And Ophiuchus, we also detect the magnetic field shown by the yellow line here. Okay, and it's easy to notice that for pipe, the cloud is elongated in this way, and the magnetic field is perpendicular to it. And for Ophiuchus, the clouds is in the same way as the pipe, but the magnetic field is also parallel with the cloud. And we believe this can help to explain why Ophiuchus can give birth of much more star than pipe. Okay. If you, probably not many of us see the aurora or the northern light, right? But probably more of us know how this northern light or aurora are formed. Right? They are actually formed by the Earth's magnetic field guiding the solar wind to the northern and southern pole region. So the fast, energetic solar wind guided by this Earth's magnetic field and moving toward the polar regions and create the polar light, right, or aurora. So same thing happened here. The gas motion, the turbulence we just see, they are not moving freely now. The velocity are actually controlled, guided by this magnetic field. Just like the Earth's magnetic field guiding the solar wind, the turbulence here will be guided by the magnetic field moving in along the field direction more, right? So when the field is parallel with the cloud, it's easier, right, for this velocity to move along the cloud and get collected and get denser and denser and form star. Okay, well, and this is our theory. Well, but for sure is we got a new player into the picture, which is magnetic field. Okay. So this is the picture we draw based on all the observation of this dense cloud. So we have supersonic motion to create these dense regions. Also gravity might further hold these dense regions. But all these motions are kind of guided by a strong, ordered magnetic field. But if you let this go forever, you never see any star forms from our simulation. Nobody can form it. So now this is the problem. Based on all the observation we have, all the physics we know, you cannot form stars. Okay. So what's the problem? So here is another simulation without magnetic field. Okay, let's see what will happen. If we want to know the problem of with magnetic field, maybe we take a look at the simulation. It's not realistic, but we can see what is going to happen if there's no magnetic field. Okay? So start with a sphere, and due to the turbulence and the gravity, they're going to concentrate, got denser and denser in the center, mainly due to gravity. Keep on zooming to the denser regions. We start to see something formed, right? It's a disk forming here. They're rotating. And while things keep on falling from outside, the center form this disk structure, which is rotating. So this is very close to what we observed, the stellar disk, right? The stellar cradle we see, we showed earlier. Okay, so this kind of tell us what might be the origin of this disk. They're probably due to the angular momentum coming from the turbulence, and they can be locked by the gravitational contraction. Under this condition, the disk will naturally form without magnetic field. The problem with magnetic field is that if we put the magnetic field in this picture with the observed strength of B field, magnetic field, we find this disk cannot form because this angular momentum and turbulence just not enough the magnetic field. As we see, the field guided the turbulence. So turbulence failed to twist the field in order to form disk. Okay, so we don't know what's happening here. It's a hot topic in star formation. On the other hand, if you take this already formed disk, right, you kind of cheat it here. You take the formed disk and you turn in, you give the magnetic field later on. It's completely cheating, but we can observe what happened, right? Artificially form the disk and you add magnetic field inside it. And this is what we see. So let me rerun this. So this white line here is the magnetic field. And if there's a disk formed already, this is going to tangle the field. So the field line becomes tighter and tighter. And this builds up the magnetic pressure at the center of the disk. So at the end, the pressure is so high, the gas cannot hold it. So the field line is kind of explosions and goes out from the two ends. And this looks very similar to the jet, which are observed, which accompanied with the disk. Okay, so this gives us some hint what might be happening there. But again, this is completely cheating, right? We skip a lot of steps. But well, these are how things go, right? You can start to study next stage, before you can find the connection between stages. And this is how scientists are doing now. Okay, here's the summary. We have lots of observed phenomenon of star formation, and we also learned some properties of this dense gas. And within this dense gas, of course, we have gravity. We have thermal pressure, but it's not so important because temperature is so low. We have magnetic field, we have turbulence, and we hope that when we put everything together, especially turbulence versus magnetic field, and somehow we can explain all these phenomena of star formation. But so far, maybe star formation rate, we can know a little bit, right? But initial mass function, the disk and jet, we are still far away from knowing the mechanism behind it. Okay, this is the current stage of star formation. And the next, right, I'm going to show you how this observation being performed. I'll show you some of the telescopes. And for star formation, we learned that we have to see through the thick and the dark clouds to reach the center. And for that purpose, as we learned, we have to go to far infrared to penetrate into the cloud to see the light emitted from the newborn baby site. Right? And one challenge of doing this to see the far infrared radiate from its newborn baby stars is that our atmosphere is a very good absorber of this far infrared. Because due to the water vapor in the atmosphere. Okay? You can understand this if you learn quantum physics in the future. The energy stage in the water molecule happen to be very close to far infrared, a pair of energy state. So they prefer to absorb this far infrared. So in order to observe this star forming site, we have to go to a site that's very dry. Okay, so you probably know you want to go to the dry side, you want to go high, right? You want to go above the cloud. Okay, so this Hawaii volcano in Hawaii is a very popular site. We can build a 10-meter scale telescope there, and Chile is the most popular site. You see lots of telescopes here, right? And actually the dried site is South Pole. The reason is it's very cold. So all the water vapors are locked into ice and fall into the ground. So the best site is actually South Pole. So if you like to travel, this can be a good career for you, right? So this is me traveling all these cool sites. Okay. And not only so, you can go high with a satellite or a flight. Okay? The problem with satellite is that you cannot launch a big telescope to the space. Like Hubble is about this size, right? 2 meters something. But for this size of telescope, it's possible to put in the airplane. And here's another airplane. Is how we go to South Pole. You have to change the wheel to the slide. It's vehicle people drive in the South Pole station. So you go to the driest place for this kind of observation. And you can bring your instrument to the site, right? Put on the telescope to collect the specific radiation you want, right? Some want for far infrared, some might want to focus on even further infrared, right? Or terahertz. So you build your own instrument and bring to the site. It's me climb on telescope to install one of the instrument. Another cheaper way to fly a telescope is to use a balloon. The problem is then your telescope will go with the wind, okay? So you have to be very carefully retreat the balloon. The telescope is right here, also about 2 meters. Okay, you might see this kind of photo before, right? There's some telescope, they're supposed to receive the radiation from space, but sometimes they do opposite. They shoot a laser beam into the space. And the reason is they try to study the reflection of the laser beam from the atmosphere to study the structure, study the turbulence within the atmosphere, right? Because these density and turbulence of the atmosphere are going to affect the incoming light from the space. By studying the atmospheric turbulence, they are able to fix this effect of turbulence of atmosphere on the incoming light, so they can get a sharper image using this so-called adaptive optics technique. So they have a mirror which is not fixed. They have a mirror which is deformable, right? They can fix the cause of the atmosphere on the incoming light to get a sharper image. Okay, and another very advanced technique is called interferometer. Well, as we said, we won't stay in the ground because we can build a larger telescope. In the space, the telescope is too small, and you need a bigger and bigger telescope to get a higher and higher resolution to look into the smaller and smaller structures in the space. Right? So for this limit of how big you can make one telescope, right? Now the state of the art is like 20 meter. Right? This is because the whole surface of the dish have to stay almost a perfect paraboloidal. If there's any deformation from paraboloidal, you're going to decrease the efficiency of the dish of collecting light. So when the telescope becomes bigger and bigger, well, you know, the gravity of the dish itself are going to deform the surface away from a perfect paraboloidal. Okay. So the new technique is that instead of building a bigger and bigger telescope, like here we see this area here is about 200 meters across. You're not going to build that big a telescope. So the technique is to build a smaller one, distribute them into the region you want, and connect them to work as one. The idea is she won the Nobel Prize of 1974, but it's only until this decade we can really develop this idea to the state of the art. Right? So let's take a short video, give the introduction of the largest telescope ever built by a human being. So again, it has to be a dry place. It's in Chile, 5,000 meters high. It's desert, very dry. And it's the furthest place on Earth from Hong Kong. Directly opposite from Hong Kong, the other side of the Earth. So now we are seeing these dishes, about 66 of them, distribute over 200 meters. You can distribute them to even farther range to mimic an even larger telescope. Largest is 16 kilometers. So you got extremely high resolution. And working wavelength of this telescope is millimeter to sub-millimeter, which is also called a far infrared, as we mentioned several times, right? To observe the cool universe. The cool here is literally cool. For those universe cold and emitting thermal emissions in far infrared. This is one of the disks. It's seen by Hubble, just a dark lamp. But this telescope can see the detail of those disks. Right? So Hubble, we see this flattened round, but with this AMA interferometer, we can see the disk actually break into gaps. Okay. And as we learned, we cannot form this disk from the simulation with all the physics we know, right? Unless we cheat like this one here. We throw away magnetic field. But we also say we can jump to the next stage. What if we put this structure into computer simulation? And can we form planets? Well, the answer is again, no, we cannot. So this is another big problem. Even you start with the disk, you cannot form planets. So the problem is, if you naively thinking is that the disk can fragment due to self-gravity locally to form planets, right? But it turns out that these local contractions will form volumes, they won't stick to each other. They can smash to each other, become finite elements. So there's a upper limit of the size this local gravity of the disk can grow into, or in the order of a meter. If it's larger than a meter, this gravitational contraction will cause them to smash each other, to turn into smaller pieces again. If you think the back, it's probably, you can appreciate this from Saturn's ring already. Right? If self-gravity is helping, then we should see Saturn's ring also concentrate to a bit larger and larger piece. But in fact, it's not. That Saturn's rings also, you can see the evidence of those icy rings. They collide each other, the pieces, right? Ice blocked, they collide each other. They don't stick to each other, but they smash each other, become smaller pieces. So no, we don't know how to grow planets, even starting from this stage. And how will we cheat again? We start from planet to us. Right? Again, I'm not the expert of this, probably more biological or chemical questions, right? But I do know a very famous experiment, which is the experiment mimic the ancient atmosphere of the Earth. Like we have methane and ammonia, waters, they put this together. And they let this gas, right, simulate the ancient atmosphere. They also applied sparks into it, which mimic the frequent of lightning in the early atmosphere, right? And they find that during the process, when they cool this gas down, and they find so-called amino acid. Amino acid is the building blocks of RNA. And so this kind of encouraging. At least some people believe this might be the initiations of the life on Earth, right? Because with the materials we collect in the atmosphere and the condition, the energy they can collect from the atmosphere, they can build the blocks of RNA. Okay. And what astronomer can help here? So astronomers are looking for us in other planets. So when it comes to alien hunt, astronomers are not very creative, right? They're not looking for transformers in other planets, but they can only starting from other lives similar to us. Right? So what they do is this future telescope. We cannot do this now. So in the future, if they can send bigger telescope into the space, 15 centimeter compared to 2.5 Hubble, or 30-meter telescope in the near infrared frequencies, they claim that they are going to be able to analyze the atmosphere of exoplanets. And maybe they can see there's some other planets outside the solar system share the same atmosphere of ancient Earth, and maybe that is another site of looking similar to us. I want to it. We know very well once a star born, how they are going to getting old and die at the end. But on the other hand, how stars can born from molecular cloud is still a big question. But at least we know that magnetic field and turbulence and gravity certainly play a role. But how they're going to collaborate with each other to form disk, give jets, and how they control the mass of newborn baby stars, and how this force can give us a planet from the disk are still big questions. So it depends on you guys, right, to devote in this direction to push our forefront of knowledge forward. Okay, thank you. I will stop here.
Questions?
I have some questions about The PowerPoint said that when the universe was first created, the first elements were helium and lithium, but not hydrogen. I think hydrogen is easier because it only needs 2 up quarks, 1 low quark, and 1 electron. And it only consists of proton and an electron. But lithium is heavier and has more components, quark components, and more electrons. But why does lithium come earlier than hydrogen?
Excuse me, what's the last sentence?
I was asking why does lithium comes earlier than hydrogen?
Lithium earlier than hydrogen. Lithium. Here. So there is echo. Excuse me. Yeah. Okay. Thank you. This is an excellent question, and actually, the formation of elements. Actually, this is a question maybe has better combined with our efforts, because for the light elements, as Professor Lee mentioned, the light elements are made of from the very initial stage of the universe, and then the heavier elements from the later stage of the universe. And exactly as you said, first there are two different questions. The one is when we are talking about the formation of elements, usually we are talking about the elements nuclei, okay? There is another question if we'd like to combine the nuclei with the electron to form an atom or not. When we are talking about the nuclei, the proton, which is the hydrogen element, is formed indeed earlier. The proton is earlier compared to like helium and lithium, etc., because the proton is made when the quarks already combine together. So the combination of quarks into the proton and neutron, which happens earlier compared to the so-called nucleosynthesis. And afterwards, there are two things happening. The one is temperature going down, and the second is the neutron wants to decay. So a finite ratio of hydrogen combines into a further light elements. So this is a story for the light elements.
So that's mean when the universe cools down, hydrogens are created and lithiums are created when the universe is created like this?
Excuse me, I have a
question in chat room. Does what we know about molecular clouds mostly come from emission line of CO?
Wow, these are very professional questions. That's right. Yeah, the reason is CO is very abundant, but how can it be more abundant than H2? H2 is the most abundant, but it's very hard to observe. H2 didn't give any radiation. It's easy to collect on Earth. The CO far less abundant than H2, but they give radiation, very easy to be observed. So indeed, we got lots of idea of cloud from CO. For example, the simulations of the turbulence I showed actually based on the observation of the CO emission. From how the CO line are widened, we know due to Doppler effect, we know what's the intrinsic turbulence velocity indeed from CO. So basically you're right, but we also based on other elements to probe different parts of the cloud. As we know, CO is easy to emit. Right? So this helps us to probe more diffuse regions. Right? So you don't need much CO to be detectable. But when you go denser and denser region, too much of emission sometimes will blur your observation. Right? So when we go to denser and denser region, we were going to change to tracers is less abundant than CO, like HCN, for example, or ammonia, for example. Right? So we use different tracer to trace different density, different temperature of molecular cloud. And of course, this all depends on theory and experiment of the ratio between the tracer and H2, right? Because we call it tracer because they can somehow trace the behavior of H2 because more 99.9% are H2. Right? So we depend on theory and models to link the tracer and H2. So indeed, because of this, when we're talking about density, for example, we are talking about order of magnitude. So I say 100,000 solar mass, right? Only order of magnitude because of the uncertainty of the link between tracer and H2. Okay, I hope this answered the question.
Yeah, I have a question. So you talked about how the universe is expanding according to Edwin Hubble. Well, if it's expanding, if it keeps on expanding, then it should keep on accelerating, right?
It is. So there are two concepts: expanding, expansion, and accelerated expansion. Okay, and now I didn't have a chance to mention that now we not only know that our universe is expansion, but also is accelerated expansion.
Right. So if it's accelerating, then doesn't it mean that at one point humans will never be able to leave the Milky Way?
No. So because the Milky Way is a gravitationally bounded system, the stars, different stars, they are attracted by gravity. They are rotating around the center. So this system is pretty stable. Yeah, there's collision with other Andromeda galaxy, another story. But otherwise, the system of Milky Way is pretty stable. It's not going to expand with the expansion of the universe. It's not going to go away. However, if we are away from our local group, a local group of tens of galaxies, if we look further, the further galaxies indeed expand with the expansion of the universe. So far, our observable universe consists of hundreds of billions of galaxies. However, if the accelerated expansion goes on as we expect from our current observation, then hundreds, tens of billions of years later, what we will see in our universe, just the local group. Everything other than the local group, further than the local group, will be gone, okay? Will be beyond our horizon, and we end up with tens of galaxies in our observable universe.
I would like to ask if we can get like the slides for today's presentation so we can have a look also by ourselves. Can you hear me?
We will send you the slide later.
Okay, thank you.
Okay, here's the next question from Nadia.
I would like to ask, like, if there are telescopes in South Pole, so why not the North Pole? Like, the atmosphere is also drier there as well.
Oh, excellent question. Okay, so the question is, why do we only build telescope in South Pole but not North Pole? It's a good question, right? Because we have a land in South Pole, it's Antarctica, but in North Pole is only floating ice. Right? And so
is it mainly because of like global warming that affects the North Pole from not building the telescopes?
Yeah, there can be another reason. Right? It's more dangerous to build telescope just above a floating ice. Right? So in South Pole or Antarctica is another story. There is the land below the 2-kilometer thick ice. So the ice is relatively more stable, but that ice is also moving. So the entire Antarctica ice cap is also moving with a speed like 1 meter per year. So you might think 1 meter per year is not much, but for observers, right, they are doing very precise pointing of the telescope to very precise position on the sky. So they can feel the motion of the ice every day. So maybe in one night, the sun parameters, they can point to Orion. The next night, the sun parameter, they will point to somewhere else. So they have to do the so-called the pointing model every night to fix the mispointing due to the land sliding, the ice sliding of the South Pole. So it's difficult to observe there, not to mention so difficult to reach South Pole, right? But this is why the biggest telescopes are in Chile, not in the South Pole, right? But in North Pole, it's not even the land. And as you said, right, the ice cap can shrink due to global warming. So, but people do go to Greenland. There's a telescope in Newcomen telescope in Greenland. And the reason to push another telescope to Greenland is that so people got even longer baseline between telescope. Right? For the one in Chile, I said the distribution of the dishes can be like 200 meters to 16 kilometers. But people actually try to link the telescope from different continents. You probably recall last year there's the people called the first photo of the black hole, right? That depends on trying to link telescope from different continents to form a telescope as big as the Earth. So by putting a telescope in as north as possible, people can further extend this distribution of the small telescope and to simulate an even bigger telescope. So people are indeed, as you are thinking in the right direction. Why don't we put one in the North Pole? People are trying to, but for safer strategy is to put in on Greenland. So you have a salty land to step on.
Question in chat room. Question is the black hole or the galaxy, which one exists first?
Oh.
Can you repeat the question?
So between galaxy and black hole, which one exists first? You first.
This is an excellent question.
Very tricky question.
I have to ask personally, I don't know. Yeah, there are all different kinds of black holes, at least three, well, at least two kinds that existing and three kinds that we are imagining of. The two kinds of black holes, one is the black holes as the dead body of a star, very massive stars. And this should be, first there are these stars and then that kind of black holes. So for this black hole should be, so after the star formation, etc. However, we also know that at the center of almost every galaxy, there are the supermassive black hole. And that supermassive black hole, probably, maybe later Professor Lee will mention more about that. Yeah, personally, I don't know what's the interplay between the supermassive black hole and the star formation and the galaxy formation. And as I heard of, so this may be an open question. And another possibility is the so-called primordial black hole that people have never firmly detected primordial black hole yet. But if they exist, they have formed in the very early on stage of the universe, well before galaxy formation. But this is just a conjecture. Professor Lee, maybe.
Yes, I totally agree. Is black hole just a stage of when density go beyond some threshold density, right? So there are different environments can help the density to reach that stage. So it depends on what kind of black hole you are talking about. Right? So when a massive star die, it is possible to reach that density. But also in the center of a galaxy, it's also can reach the stage. And for massive star, are you talking about the star forming within galaxy, which is most I'm talking about today? But it's also possible that in the earlier time of the universe, star can form without a galaxy being formed at the beginning, right, at the first, because in early time, the density is so high. And that star might also be able to reach the density threshold of black hole. Right, so this really hard to answer.
Next question. Jane Kid, you can ask now.
Dr. Lee, you told that the turbulence in the cloud will make the formation of baby star difficult, but the turbulence in the Ophiuchus, is that the right pronunciation, or do you get my meaning? The Ophiuchus is more favorable for forming new baby stars, but its turbulence still affect it and make it difficult to form. But for the pipe, there is also a magnetic field, but it is, well, I puzzle if it means it is less favorable for forming the stars, or that the two magnetic field also make the star formation difficult. So is it that the Ophiuchus is more favorable than the pipe, or that the two cloud also difficult for forming the stars?
Okay, these are excellent questions. Right? It's probably my fault to didn't explain this clear enough. Turbulence, they kind of connect energy, right? They are going to against the cloud from globally contraction due to self-gravity, right? And we learned this. But at the same time, I also mentioned that because turbulence is supersonic, so they can create local shock, high density shocks, like the jet fighter, supersonic jet fighter can create in our atmosphere. So the supersonic turbulence can also locally create this high density part. And this can locally form stars, right? Because you don't need the total mass of the entire cloud to form star. The cloud is so massive, right? Millions, even hundreds of thousands of solar mass. So you can locally compress them to form star. So turbulence has two functions. One is prevent the cloud from globally contraction, but locally, because they're supersonic, they can help to enhance local density and also enhance star formation locally. So this is turbulence. And the magnetic field in the Ophiuchus cloud come to play in such a way. The cloud, the magnetic field orientation will channel the turbulence. And so the turbulence motion will not be isotropic anymore. They tend to be guided by magnetic field. So they tend to move in one direction. Okay, just like the solar wind guided into the northern pole by Earth's field, the cloud field can guide the turbulence motion. Okay. And when the field is along the cloud axis, okay, the collection of mass due to the turbulence motion is more efficient. Right? Imagine if you want to accumulate gas from an elongated cloud, how you want to collect the gas. You want to collect them along the long axis, which is easiest, more efficient. You got more mass to accumulate along the longer axis. Right? Along the shorter axis, you don't got much to collect. Right? So when the field is along with the longer axis, and they can guide the turbulence to collect the gas in a more efficient way. But when they are perpendicular to the axis, there's not much gas to collect from.
Okay, next question. So Yunho, you can ask now.
Yes, I want to ask, you have mentioned that the universe expanding. Does that mean the orbits of the bodies are like enlarging as well?
You mean the orbits of
the bodies like galaxies or systems?
No. So this is actually a very good, tricky question that at the so-called galaxy cluster scale. So if you go beyond some clusters of galaxies, then the space expands with the universe. But if you think about galaxies and smaller scales, like us, like atom, so this smaller scale from the galaxy all the way down to the atom, they are some bounded system, either bounded by gravity or bounded by some electromagnetic force, etc. So there are forces to push back, okay, to push us back. So they are not expanding following the expansion of the universe.
So the expansion of the universe does not carry anything other than the boundaries of the universe itself.
I'm not very sure about what do you mean by carry, but we can imagine what happens by we pump air into a balloon, and that balloon is expanding, and then if you have 2 points on the balloon, if you put two things on the balloon, unless they are tied by some strings, so unless they are bonded, otherwise the matter on the balloon will expand. Our expansion of the universe is exactly like that, except that we are 3-dimensional and the surface of the balloon 2-dimensional. Does that answer your question?
But if you pump air into a balloon, that means
yes,
the matter of the balloon itself will space out, like the distance between the matters will increase. But
right.
Does that mean the system, the distance between systems and systems will increase as well?
So by purpose, I was saying that unless you tie 2 objects together, which are on the surface of the balloon, I mean, physically you put 2 objects together, which are tied by a string, okay, onto the balloon, then they will slide, okay? They will slide on the balloon, will not expand together with the balloon, okay? That is similar to the bonded system, like my hand and also this mouse, okay? They are tied, and imagine I put them onto the surface of the balloon. They are not going to expand together with the balloon because of the tie here. And here by the tie, I mean bounded by some force, like gravitational force or electromagnetic force. Yeah, in that case, that system is not going to expand together. Indeed, okay. They feel a force because of the expansion of the universe exerted on them, and sometimes the astronomers call it Hubble flow, flowing with the expansion. At the same time, is tied by gravity.
Thank you.
Hello. So I have a question. I want to ask, is time the 4th dimension?
Excellent question. Yes or no? That depends on what do you by the 4th dimension, okay? Our 3 dimensions, so they are our everyday experience, and time. So why? First of all, why we tie our 3 dimensions together to 3 dimensions? Yeah, what do I mean is why? For example, up, down, and also front, back. Okay, why these 2 dimensions? Why these 2 dimensions are we consider them very close together? This is because of symmetry. Okay, these 2 dimensions are fundamentally they are the same. They are related by rotation. Okay, this is why we talk about space dimension. The 3 dimensions we talk all together, and time is actually also related to space with a symmetry, and that symmetry was known as special relativity, discovered by Einstein 100 years ago, that if we talk about a moving observer compared to an observer not moving, actually the space and time between an observer moving and not moving is very similar to the 3 space dimensions that time of one observer can project into space of another observer. And that is the so-called time dilatation and space contraction, a whole lot of things following special relativity. And because of that, although our experience of time is so different from space, we sometimes put time together with space to 3 plus 1 dimension of space-time, put space and time together to be space-time. Because in special relativity, space and time are unified. Thank you for your question.
Thank you.
Okay, Chong Yi Lam, you may ask.
Actually, the people say that the creation of the universe was because of the Big Bang. But what about the Big Crunch, which they say will be the end of the universe?
Thank you.
So,
This is, yeah, thank you. This is an excellent question. Actually, there are two parts of the question. Number one is the creation of the universe Big Bang? Yes or no? Actually, when people are talking about Big Bang, they mean actually two things. The one thing is when after the so-called inflation, our universe become hot again, and that is usually known as the hot Big Bang. And when scientists talk about Big Bang, usually they talk about that hot Big Bang, that after inflation, our universe become hot again. This is because the absolute beginning of our universe, so far, we have no trace of how to study it in cosmology. So it's not so far a thing that we can study. All right. So this is about the Big Bang and about the Big Crunch. This is a conjecture. So so far, we don't know if Big Crunch will happen or not. The Big Crunch is a stage, is a hypothesis that if everything will go back together and to crunch within one extremely infinitely high density. And so far, there is no trace of Big Crunch. 30 years ago, it was a very popular theory, but now it is not so popular because of the discovery of dark energy. Dark energy, the discovery tells us that our current universe is not only expanding, but accelerated expansion. That means the expansion is not likely to decelerate and crunch again. So if our dark energy is indeed the dominant energy source of the future, there will not be big crunch, but rather it will be a very lonely state that there are a handful of galaxies within observable universe and accelerated expansion.
Okay, Chungka Kid, you can ask now.
Yes, I want to ask, if the universe is expanding, so can it stop the collision of Milky Way and Andromeda?
Excellent question. Yeah, so first of all, it is between the universe and the galaxies, all right? And in the universe side, the Andromeda galaxy is within our local group that I mentioned when talking about another question. That so us and the Andromeda galaxy, so our distance is not really expanding, and so there are peculiar motion that the galaxies are moving themselves and also attracted by gravity themselves. So the expansion of the universe will not prevent the collision. Professor Lee, do you have anything to add?
Yes, right. Just like those simulations we showed, right? Under the existence of dark energy, still those cosmic web can form, right? Those are the local winning range of gravity, right? Even with the existence of dark energy. So it's an energy. Right? The energy has a limit. If you build a rocket, can leave the gravitational grab from the Earth, doesn't mean that rocket can take off from any other planet. Right? It has a limit. Sometimes gravitational force wins, especially locally.
Oh, Bowen, you can ask now. Bowen, you can try again.
Yeah, okay. Okay, I have two questions. What's the nearest known black hole in our galaxy? And if we do know the black hole, why can't we transport waste into that black hole so our planet won't have to deal with global warming and like negative stuff anymore?
First, the question, so I'm trying to answer, but actually I'm not the person to answer since I, so my main field of study, the whole universe, But first of all, there is a black hole, supermassive black hole at the center of our Milky Way. I'm sure this is not the nearest. Actually, I don't know which is nearest or which is the nearest observed.
Oh, I don't know either. Yeah. What we are sure is there's one black hole in the center of the galaxy. For that one, the distance is known for better. But as we discussed, there's a different way to form black hole. Right? Some black hole, they are not formed in the center of the galaxy, but they are just dead body of a massive star. For that kind of black hole, and because they are black, it's just very hard to observe them. Not impossible, right? You might be able to observe them through gravitational wave, but it's hard to decide the distance. And what's the second part of the question about global warming?
If we know that black hole exists, why can't we transport waste into it so our planet won't have to deal with global warming and negative stuff anymore?
Oh, waste?
Yeah,
well,
waste.
It might take more energy to ship them to a black hole. Yeah. Let me give an example. Even though we don't know the nearest black hole, but we do know the nearest star. Well, nearest star is the sun, right? The second nearest star is actually 4 light years away. So if you want to transfer our waste to this star, you need to move in the light speed for 4 years, right? So it's you probably just dump them to Jupiter, maybe. It'd be easier.
Okay.
Let me add a little bit that this is a very interesting question in two senses. The one is in technology. So if we really calculate the cost, for sure it's very difficult. It doesn't emit more heat when we launch the rocket, right? But if we just think about it as a question in principle, it's a very interesting question. That for some of the black holes, actually, if you throw garbage into the black hole, so you get energy, and then you solve two of the problems. One is garbage collection, and another is you get energy. So in principle, this is a very interesting problem.
Okay, thank you.
Hero, you can ask now.
Okay, so I have a very so like I've heard of black hole solar systems. Like the star in the center of the system is actually a black hole, but there are planets around it. And I heard that some of these planets might actually harbor life. So, are there any neutron star systems? If so, can they also harbor life? If black holes can already do so, why not neutron stars?
First of all, I don't know. In principle, it's possible. I didn't know if there is any observation of a neutron star solar system. But very interestingly, recently, there is a news about the discovery of a white dwarf system with a planet. Yeah, so if white dwarf can do it, sun can do it. So every reason points to the neutron star likely can do it, but I don't know examples. But actually, there are neutron star binaries. One neutron star rotating around another neutron star.
Okay, next question. Matthew 9, are you here?
Yes, I'm here. I have a question about your about the earlier presentation. You talked about the observable universe is because the objects are giving off light, and then those lights have not reached us yet. But I've also learned that because of the cosmological inflation, those lights are being infinitely redshifted. So how do these two concepts relate to each other?
Thank you. This is an excellent question. So inflation is highly related to our current horizon. That's the part of the universe that we can see, observable universe. And exactly as you said, that during inflation, if inflation happens long enough, so if there are, you imagine light at that moment, that light or gravitational wave or whatever existing at that time will be infinitely redshifted. I mean, long enough redshifted, as long as inflation happens long enough. However, that part is outside our observable universe. So this is related to your question that inflation prepares for us an extremely large universe, could be so many orders of magnitude greater than our observable universe. So what you mentioned, infinitely redshifted, is actually outside of our observable universe. And in our observable universe, there are also something infinitely redshifted, which is light emitted on the boundary of the black hole, from the horizon of a black hole. But that's another story, not the universe.
Let's do one more question. Wong Si-Jit, are you here?
I'm here.
You may ask now.
Okay, so I'm asking a really simple question. What if there's no universe?
A really simple question is a really difficult question, okay? So first of all, universe is our space-time, all right? That's the playground that not only we exist, but also the playground that we understand physics. If we don't have space-time, we don't have the universe, how do we understand that physics? In terms of what do we understand the physics? This is actually, but we cannot answer so far. This is because so far, up to the most up-to-date theory, like quantum gravity string theory, so space and time are still the fundamental objects in the study. So if we don't have space-time, we don't have what to study. There are conjectures that space and time get emergent, okay? Emergently arises. For example, Hawking's conjecture of the quantum creation of the universe. There are such conjectures that the universe created from nothing. But so far, on the one hand, there is no firm evidence about that conjecture. On the other hand, there are so many problems about that so far we are not sure.
Right. Okay. Thank you very much for your questions, and also thank you very much for Professor Lee and Professor Huang to give us a very inspiring talk today. All the participants, please notice that we will upload all the slides to the Hong Kong AG website after we have sought the permission from the two speakers. So you may visit our website to see whether we can get the permission from the speakers to upload all the slides, right? Okay, thank you very much and have a nice weekend. Bye-bye.